Welcome back to Big Data. In this lecture, we are taking a deep dive into one of the most fundamental ideas in distributed systems, the CAP theorem, and the trade-offs it forces every database architect to make. Modern applications don't run on a single machine anymore. Data is split, replicated, and spread across many servers, sometimes across continents to handle massive scale. But spreading data out creates a problem. When the network between servers isn't perfect, what should the system prioritize? That's exactly the question the CAP theorem answers. The CAP theorem was first proposed by computer scientist Eric Brewer in 2000 and formally proven 2 years later by Seth Gilbert and Nancy Lynch. It's become one of the foundational principles for understanding trade-offs in distributed database design. CAP stands for three properties every distributed system must reckon with: consistency, availability, and partition tolerance. Here is the central idea. A distributed database can only fully guarantee two of these three properties at the same time, never all three at once. Whenever a network partition happens, the system has to choose: stay consistent or stay available. Understanding that trade-off is the whole point of this lecture. Let's start with consistency. It means every read operation returns the most recent writes. In other words, every node in the distributed database shows exactly the same view of the data at any given moment, no matter which server answers your requests. Think about a banking system. Your account balance needs to update the instant you deposit or withdraw money, whether you check your balance at an ATM, on your phone, or by calling the bank. Every one of those views needs to reflect the same or the exact same number immediately after the transaction. That is consistency in action. Next, availability. This means the system stays operational and keeps responding successfully to reads and writes, even when parts of it are failing. In an available system, every request gets a response. Picture an online store during a massive flash sale. Traffic spikes far beyond normal levels, and parts of the infrastructure may be struggling. But the system keeps serving customers, even if that means showing slightly outdated stock counts for a moment, rather than showing an error page or going offline entirely. Finally, partition tolerance. This means the system keeps functioning even when communication between nodes breaks down. When a network failure splits the system into two or more groups of servers that temporarily can't talk to each other. Think about a global social media platform with data centers on different continents. If a network issue cuts communication between, say, the service in Africa and the service in Asia, users on both sides should still be able to post, like, and scroll. The platform keeps running on each side of that partition. Put these three together and you get the CAP triangle: consistency, availability, and partition tolerance at each corner. In theory, a distributed system can only really sit close to two of these corners at once. And because network partitions are simply a fact of life in distributed systems, the real choice most architects face is between consistency and availability. Systems that prioritize consistency and partition tolerance are called CP systems. MongoDB, in its default configuration, is a classic example. It emphasizes consistency and partition tolerance, meaning during a network partition, it may reject some requests rather than risk returning stale or conflicting data. Systems that prioritize availability and partition tolerance are called AP systems. Couchbase and Cassandra are good examples. They keep responding to requests even during a network partition, accepting that different nodes may briefly disagree, with data becoming consistent again once the partition heals. Traditional relational databases were largely designed as CA systems, prioritizing consistency and availability, assuming the network simply wouldn't fail. In practice, real distributed systems can't fully avoid partitions. which is exactly why so many modern databases are explicitly built as CP or AP instead. Let's put all three side by side. CP systems, like MongoDB, sacrifice some availability to guarantee accuracy. AP systems, like Cassandra, sacrifice some consistency to guarantee uptime. CA systems, like traditional relational databases, assume a reliable network and prioritize path, consistency, and availability, which only really works when partitions are rare or the system isn't distributed at scale. So, how do you choose? It comes down to your application's need. A banking system will almost always favor consistency. You can't afford incorrect balances. A social media feed or shopping cart will often favor availability. A slightly stale view beats no response at all. A multi-region app must handle partition tolerance. One common misconception: CAP doesn't mean you permanently give up one property forever. In practice, most systems behave consistently and stay available during normal operation. The trade-off only kicks in during an actual network partition, which is why CAP is really about behavior under failure, not everyday performance. To recap, the CAP theorem says a distributed system can guarantee at most two of consistency, availability, and partition tolerance at once. Since partitions are unavoidable at scale, the real trade-off is almost always between consistency and availability, and that choice should be driven by what your application actually needs. The CAP theorem is a great starting point, but it is not the whole story. In our next lecture, we will build on it with two more theorems, Bayes and Paselic, that give an even richer picture of how distributed databases really behave. Thanks for watching this lecture on the CAP theorem, part of our Big Data course. See you in the next session, where we will dig into Bayes and Paselic.